Hello students, welcome to online maths classroom. Today in this video, we will finish continuity and differentiability, the topic number 5 of your NCERT. We will finish miscellaneous exercise question number 1 to 23. So let us start with it. Question number 1 of your miscellaneous exercise is, you have to differentiate 3x square minus 9x plus 5 raised to power 9. Okay, so I think this is a very simple question. Here you have to take this y is equal to this complete term. And what is dy by dx? It is 9 times this function. Take it as x. Say it is like x raised to power 9. So it will be like 9x raised to power 8. Okay, so 3x square minus 9x plus 5 raised to power 8 into ddx of 3x square minus 9x plus 5, which will be coming as your 6x minus 9. Okay, and rest of the thing is same. And you can take more things common. You can take 3 common out of this, and it will be 27 times the product of these two terms. Second is sine cube x plus cos raised to power 6x. So again, the power rule will be used, and you are all familiar how to take the derivative. It is like 3 sine square x into ddx of sine x is cos x, and it will be 6 cos x raised to power 5, and ddx of cos x is minus sine x. And you can take 3 sine x cos x common, and the rest of the term is the non-common part. Number 3 is again function raised to power function, which can be differentiated by taking log both sides. So it becomes log y is equal to log of 5x raised to power 3 cos 2x, which can be written as like your 3 cos 2x into log 5x. Now differentiating both sides with respect to x, it will be 1 by y dy by dx is equal to 3 times your product of two functions. So it will be cos 2x into ddx of log 5x plus log 5x into ddx of cos 2x. So log 5x will be like 1 upon 5x into ddx of 5x, that is 5, and the derivative of cos 2x will be minus sin 2x into derivative of 2x, that is 2. So after multiplying and cross multiplying, you have to take, you know that in logarithmic differentiation type of question, you have to take this y to other side and substitute the value of y from the very first equation, and you can get the answer. Number 4 is differentiate sine inverse x root x, where x is lying between 0 and 1. Okay, so that actually means it is sine inverse x raised to power 3 by 2, as 1 power of x and half power of x will give me this result. Now we know what is the derivative of sine inverse x. It is 1 upon under root 1 minus x square. So here this x is this, so x square means it is x raised to power 3 by 2 whole square, and ddx of your x raised to power 3 by 2. Okay, so it will be like this will be your 1 minus x cube under root into 3 by 2, power rule will be using here, 3 by 2 times x raised to power half, and which can be settled to get this answer. Number 5 is a function which can be differentiated up by applying the quotient rule. I think there should be no doubt, as it says that denominator whole square, denominator time ddx of numerator. You know cos inverse x by 2 will be having derivative as minus 1 upon 2 minus 1 upon under root 1 minus x square, and ddx of your x by 2, and minus cos inverse x by 2 ddx of, you know, root x term is taken as 1 upon 2 root x into ddx of your 2x plus 7. And after the adjustment of each power and taking LCM, you can get the answer as your 2 upon this complete term. Okay, and the further reduction can be done, and the complete term can be solved. This is the numerator upon 2x plus 7, which is minus, say you can take LCM in the numerator also, and can settle the terms in the denominator, and this question can be reduced to this form. Question number 7 says log x log वही बंद हो जाता है. Number 9 is sin x minus cos x raised to power sin x minus cos x, x lying between pi by 4 and 3 pi by 4. Now again it is function raised to power function. So most suitable method is taking logarithmic differentiation. So log y is equal to your log m raised to power n can be written as n log, and this is m. Okay, so let us take the derivative. It will be 1 by y dy by dx. This function, first function, d dx of this complete is 1 upon sin x minus cos x into d dx of sin x minus cos x is your, we can take it as like d dx of sin x will be cos x, and your minus cos x means cos is having derivative as minus sign, so it will be your plus sin x. Okay, so this is how we take the derivative. Plus log sin x, second function, we log sin x minus cos x into d dx of your sin x minus cos x. Okay, so this is how we can take the complete derivative, and after taking your cos x plus sin x common outside, you will have this complete term. After solving it, take y to other side. Okay, replace the value of y and you will get the derivative dy by dx as this complete term. Number 10 is there are four functions which are totally different from each other, like x raised to power x, x raised to power a raised to power x plus a raised to power a for some fixed a positive and x positive. Now as all these functions are different, so for taking derivative I have to separate all the terms. Okay, so first one is like this is x raised to power x. So you know x raised to power x is to be differentiated using logarithmic differentiation because it is function raised to power function. So we will take log both sides. So it is log u, derivative of log u is equal to d dx of x log x using product rule. I think earlier we also have done it. So it becomes du by dx as u times 1 plus log x. So d dx of x raised to power x is x raised to power x times 1 plus log x. And derivative of x raised to power a can be done as power rule as a x raised to power a minus 1. And derivative of e raised to power x you already know. It's a formula e raised to power x log to the base e of a, and last one the derivative is 0. Okay, and then replace the value of in dy by dx of this function, and other two values are already differentiated values. So this is the complete dy by dx. Number 11 is x raised to power x square minus 3 plus x minus 3 raised to power x square for x greater than 3. So again, you know that it is again a function raised to power function, but I cannot take the log like it is the sum of two terms. So I separate it as this, take this as eu and this as we used to do in logarithmic differentiation. Okay, and dy by dx will be your du by dx plus dv by dx. So take this u as separate function, take log both sides. Now the derivative I think is not going to give you trouble. It is x square minus 3 into 1 by x plus your log x into derivative of this term is 2x. And take u to other side, put all the values, and you'll be getting the du by dx as this complete. Similarly, v can be differentiated by using logarithmic differentiation. So take your this log v is equal to your x square times n log m. After taking n log m, it is x square times log of x minus 3. So the derivative is 1 upon v dv by dx, and it is using product rule x square, and this is 1 upon x minus 3 into d dx of x minus 3 is 1 plus log x minus 3, and d dx of x square is 2x. Now take all the terms v to that side, take a little bit of LCM and solution, and then you will get dv by dx as after replacing v as this complete. Now you know you have to put back both du by dx and dv by dx back here, and no need to solve it, just replace whatever you have got here, and this is dy by dx. Number 12 is dy by dx if y is equal to this function and x is equal to this. Now you know that it is the parametric form. So you remember how to do it. You will take dy by dt, okay, and then dx by dt, and to find dy by dx, I'll divide dy by dt by dx by dt. So it is not going to give you trouble because the very first function is 12 times this is 0 and derivative of cos cos is minus sign, so it will be plus sin t. So it is 12 sin t. And this one is 10 times derivative of t is 1, and it is derivative sin is cos, so 1 minus cos t. So when you will divide, you have to reduce it. So sin t can be opened as 2 sin t by 2 cos t by 2, and this has 2 sin square t by 2. After cancellation, you will get it as 6 by 5 times cot t by 2. Number 13 is dy by dx if y is equal to sine inverse x plus sine inverse root 1 minus x square. Now it can be easily differentiated. So sine inverse, it is 1 upon root 1 minus x square, and this sine inverse will be your 1 upon, because here x is this, so 1 upon under root 1 minus this x square into d dx of this root 1 minus x square. Okay, so this is same, this term is also same, and you know that derivative of your root x type of thing is 1 upon 2 times root x, like this, into d dx of 1 minus x square, that is minus 2x. Okay, and after rearrangement and taking LCMs, we can reduce that. This result is giving me the value as 0. Number 14 is a very good question. If x times root 1 plus y times root 1 plus x is 0 and x is between minus 1 and 1, you have to prove that dy by dx is minus 1 upon 1 plus x whole square. Now it's again an implicit type of function. You cannot separate like x and y together. So I have to simply start with the derivatives. So what I will do is this is an expression, you first simplify it and then take the derivative, so that otherwise I think these things are going to give you very large results. So it's better to express this question, take one term to other side like minus y times root 1 plus x. Firstly, remove the root by taking the square. Open all the terms, make factors to this side. X minus y, x plus y is equal to, take minus xy common, it is x minus y. Cancel x minus y, okay, as it is not equal to 0, okay, because x is not equal to y. We get x plus y as minus xy, okay, and you have to just now express it as y equal to something. So take this, both these minus xy and x to one side, take y common, okay. You have to take y and minus xy to one side, okay, so it will be y plus xy and this x to other side as minus x. So y will be minus x upon 1 plus x, which can be now I think by taking the quotient rule, it can be easily differentiated like 1 plus x whole square into 1 plus x dx of x is 1 minus, this minus sign should be taken into consideration, okay, and minus x times d dx of 1 plus x, which is 1. So it becomes minus 1 upon 1 plus x whole square. Number 15 is, if x minus a whole square plus y minus b whole square equal to c square, for some c greater than 0, prove that 1 plus dy by dx square raised to power 3 by 2, this complete term by d square by dx square is a constant independent of a and b, okay, means the value you will get will be a constant term and it will not be including a and b. So let us start with it. I think this is again a question in which you need a little bit simplification. You have to open it before taking the derivative, and also this is an implicit function, so you will not be able to get again x and y separately. So instead of, I think, opening it, the better idea would be I will go for differentiation directly, like from here. So it will be 2 times x minus a, d dx of x minus a is 1, and it is 2 times y minus b, d dx of your y minus b will be dy by dx, and this is constant, so derivative is 0. Now take this side to other side, minus 2 times x minus a, 2 cancelled, and dy by dx will be minus times x minus a upon y minus b. Now again you need to, because the second derivative is required here, so again I'll take the derivative using quotient rule. So take minus sign outside, y minus b whole square, it is y minus b times d dx of this x minus a is 1 minus x minus a d dx of y minus b will be your dy by dx, okay. Now since dy by dx is not required, so you will get back that value of dy by dx from here, number 2. So replace it back here, okay. Take the LCM, see it will be y minus b plus, this becomes x minus a whole square, and this minus and minus will be plus. Take LCM, it will be minus is outside, so y minus b whole square plus x minus a whole square, and this y minus b will come down and it will become y minus b whole cube. Now this term, you see, come back to your original question, it is your c square. Okay, this term is your c square. So it becomes, minus is outside, so it becomes minus c square upon y minus b whole cube. Okay, so by 1 you will get this value. Now putting the values of dy by dx and d square y by dx square from your number 2 and number 3 in the given expression, you will get this value. Now come back to this here, 1 plus dy by dx whole square raised to power 3 by 2. This is your required expression, and in it you replace all the values that you got, this dy by dx, okay, and then this d square y by dx square. After taking LCM, you will again find that denominator can be expressed as c square and raised to power 3 by 2. Okay, this y minus b whole cube gets cancelled and denominator with minus c square. So this becomes c cube minus c cube, as 2 gets cancelled. So c minus c cube by c square is minus c, which is, you know, is a constant independent of a and b. Number 16 is if cos phi is equal to x cos a plus phi, with cos a is not equal to plus minus 1, prove that dy by dx is cos square a plus phi upon sin a. So again, it's better suggested, express it as x is equal to cos phi upon cos a plus phi. Now why I expressed as x equal to, not y equal to, because you see that when I express it as x equal to, the terms are just this side only, y terms will be there. Okay, so differentiating now, you can apply the quotient rule. It's not a very difficult question. You are well familiar with quotient rule. So after applying the quotient rule, you will find that this question reduced to sin a upon cos square a plus y. Okay, now you know that I don't want dx by dy. As you know, this function is x equal to something, so I have to take the derivative. X is a function of y, so I have to take the derivative as dy of x. So dx by dy I will be getting. And to find dy by dx, I'll take the result. Number 17 again is a parametric form. X is equal to e times cos t plus t sin t, and y equal to e times sin t minus t cos t. And we are required to find d square y by dx square. Now you know how to do this question. You'll first find dx by dt. So it is very simple. By finding the derivative of dx by dt, you will get it as your at cos t. And again, then you will find dy by dt. Okay, and that will turn out to be at sin t. And dy by dx will be your dy by dt by dx by dt, which will be your tan t. So again, the derivative can be done by retaking the derivative here. So it is ddx of dy by dx again, that is derivative of tan t, which is secant square t into dt by dx. Okay, so dt by dx, you will re-put the value from here as it is dx by dt. So take 1 upon et cos t, that is reverse, you will get it as the term here. So secant square t, and it is your secant t cos t, take it to numerator. So it will be secant t upon at, so it becomes secant cube t upon at. Number 18 is your if fx is equal to mod of x cube, show that f double dash exists for all real x and find it. Okay, so given your function, you know the definition of the mod says that mod x is x if positive, x is greater than or equal to 0, and is minus x if it is negative. So mod x cube will be like x cube for x greater than or equal to 0, and minus x cube if x is less than 0. And the derivative will be like for this, for x greater than 0, it will be 3x square, and for less than 0, it will be minus 3x square by the definition. Okay, and x equal to 0, we can't, this here 0, we can't write the value of derivative, because usual rule of derivative says that x equal to 0 will be this partitioning point. Okay, like the 0 of this function. Okay, 0 value. So what we need to do is the double derivative. If I want to go for x positive, it will be 6x, and For it will be minus 6x, like for x less than 0. And the double derivative for all x greater than 0 and or less than 0 will be there for all x belonging to R except x equal to 0. We can find that the double derivative is existing. Okay, but we are supposed to find for all real x. That means 0 is also included in that. So that means I have to now check the derivative for x equal to 0, because I am able to find that for this x positive and x negative. I am having the first derivative as 3x square, second as 6x, and the first derivative as minus 3x square and second as minus 6x as per definings of x greater than 0 and less than 0. But I have to discuss the differentiability at x equal to 0. And for that, I'll use that result like left hand derivative and right hand derivative. As the function is towards positive side, it is behaving different, and towards negative side, it is behaving different. So left hand derivative, if you remember, it is limit x approaches to 0 from negative side, f of x minus f of a upon x minus a. So a here is your 0. So it is f of x minus f of 0 upon x minus 0. So f of x, you know, for your left hand derivative means it is defined as minus x cube, and this is f of 0 will be 0 upon x. So I'll get it as minus x square. After applying the limit, it comes out to be 0. So no need to go for 0 minus h, that kind of result. Similarly, the right hand derivative will be fx is as your x cube. So x cube minus 0 upon x, that is x square, which is always 0. Okay, so left hand derivative, right hand derivative, both are 0. Same. So function is differentiable at x equal to 0. And the first derivative will be your f dash 0 equal to 0. We say derivative at 0 is 0. Now the first derivative is existing at x equal to 0. Now I need to check the second derivative. So see, the first derivative formula was fx minus f0 upon x minus 0. The second derivative formula, like left hand derivative, will be your limit x approaches to 0 from negative side. It will be, instead of fx, it will be f dash x minus f dash 0 upon x minus 0. Okay, so f dash x, you know, it is your for this x less than 0, it is minus 3x square minus 0 upon x, which after solution will give me 0 result. And right hand derivative will be like limit x approaches to 0 from positive side, f dash x minus f dash 0 upon x minus 0, which will, after placing the value, will give me the value as 0. So both this second derivative is also existing for left hand and right hand, and both are same to 0. So that means function is differentiable at x equal to 0, and the double derivative at 0 is again 0. So what we conclude, that this double derivative f double dash x is existing for all real, and this your f double dash x is 6x if x is positive and minus 6x if it is negative, and the value of this double derivative at 0 is 0. Number 19 is, using mathematical induction, prove that ddx of x raised to power n is nx n minus 1 for all positive integer n. So you did it in your last class, you know, induction process. Let p n this statement. So first is put n as 1. So it becomes ddx of x power 1, that is your 1. Okay. So your, you know, that a derivative of, to this side, put, we are putting the values, it is 1 into x raised to power 0, that is again 1. Okay. So which is true, that is p1 is true. So next step is, let us assume pk is true, that is ddx of x raised to power k is your kxk minus 1. Okay. Now ddx of x raised to power k plus 1, which is your ddx of, now break this as x raised to power k into x, because you remember we have to use this value. So ddx of, as it is the product rule, okay, don't get confused here, you have to apply the product rule, because derivative results are applied here. So it will be like ddx of x raised to power k into x plus x raised to power k into ddx of x. Okay, so ddx of x raised to power k, you will put the value from here like kx raised to power k minus 1, okay, into x plus x raised to power k, and ddx of x is 1. So it is kx, as x powers can be added. So it is kx raised to power k plus x raised to power k. Take x raised to power k common, and it is k plus 1, that is pk plus 1 is true. Hence, by principle of induction, this result is true for all positive integers n. Number 20 is using the fact that sine of a plus b is equal to sine a cos b plus cos a sine b, and the differentiation obtain the sum formula for cosines. Okay. Now, see, this is a very good question. You have to convert sine a plus b, which is given as your formula, sine formula, you know it. You have to change this formula to the sum formula or cosines. Now, what I'm going to do is assume a and b are functions of x, and we have to differentiate both sides with respect to x. We'll start from here. Okay. So it becomes sine of a plus b is cos of a plus b, and ddx of a plus b will be like dA by dx plus dB by dx, as they are outside the function. You know, if I have to take the derivative of y with respect to x, so it will be written as dy by dx. Similarly, it will be d upon dx plus dB by dx. And to this side, it will be like you have to apply ddx of sine a into cos b plus your sine a into ddx of cos b. Similarly, cos a ddx of sine b plus sine b ddx of cos a. Okay. So this will be like your cos a, okay, dA by dx into cos b plus sine a, okay, and then you have to take your derivative of this side cos b as minus sine b dB by dx minus your sine a dA by dx, okay, into sine b plus cos a, and this is cos b dB by dx. Okay, so what I will do next is I'll separate the terms of dA by dx and dB by dx. Okay, now these terms separation, what it will give me, that cos of a plus b, this dA by dx plus dB by dx will be equal to your cos a cos b minus sin a sin b, and you see this is same, so it is times dA by dx plus dB by dx. When we will separate it, we will find that a common thing is getting common out of these two terms, so it becomes like this. So this term will be cancelled with it, and or we can see by dividing with dA by dx plus dB by dx, I'll get cos a plus b equal to this. And you know, the formula of sines, sum of sines is converted to formula of sum of cosines. Number 21 is, does there exist a function which is continuous everywhere but not differentiable at exactly 2 points? So yes, there exist some functions which are like this. So these functions can be taken as the sum of two modulus functions. Like I can take x minus 1 mod plus x minus 2 mod, because I need 2 points. And the 2 points will be the zeros of these functions. Like the zero of this function is x equal to 1, and for this it is x equal to 2. Okay. Now these two real numbers at x equal to 1 and 2, you will divide this complete real number system as these intervals, like from minus infinity to 1, 1 to 2, and from 2 to infinity. Okay. So you will break it in 3 intervals. From minus infinity, you know, it is open to this side to 1, 1 closed, then from between 1 and 2, and then between this closed interval to this side 2 and 2 to infinity, because we will break this complete two real numbers which we are checking at the differentiability from minus infinity to infinity. The complete system is to be divided in 3 intervals, as there are 2 points. If 1 point is there, it will be divided in 2 intervals. Now for c x less than 1 equal to 1, this x minus 1 is less than equal to 0, it is negative, and this second one is also negative. So I'll get function as fx, means the fx as both minus times x minus 1 and minus times x minus 2, as I know that this mod of x is minus x if x is less than 0. Okay, and after solution I can take it as 3 minus 2x. Okay, and now between 1 and 2, what is going to happen? You see, between 1 and 2 means say like 1.5. This will be my result as positive, x minus 1 is positive and this x minus 2 is negative. So like my fx will be your x minus 1 minus x minus 2, that is your 1. And for the last interval 2 to infinity, okay, say greater than 2, I take say as 2.5. So this will be positive, this will be positive. So both added will give me 2x minus 3. Okay, now the three values of fx given by this equations 2, 3, 4 are polynomial functions and constant, and hence they are continuous and differentiable for all real values of except this x, except possibly at this partitioning points x1 and 2. So let us check it. So firstly I'll take the discontinuity at x equal to 1. So you can check the left hand limit, okay, the right hand limit, and you will find they both are same, and the value of function at this point 1 is also same as both these values. So function is continuous at x equal to 1. Now since for differentiability you need a continuous function, so continuity is there, I will check the differentiability at x equal to 1. And this will be checked as left hand derivative at 1 and a right hand derivative at 1. So left hand derivative is limit x approaches to 1 from negative side, f of x minus f of a upon x minus a. This is the formula. So a here is 1, so it is f of x minus f of 1 upon x minus 1. Okay, f of x is your 3 minus 2x and f of 1 is minus 1 upon x minus 1. And after solving you will get it as minus 2. Similarly, right hand derivative will be f of x minus f of 1 upon x minus 1. So it will be your 0. Okay, so you find LHL is not equal to RHL. This LHD is not equal to RHD. So that means function not differentiable at 1. So it was continuous, not differentiable. Similarly, we can check the continuity at x equal to 2 as per defining. So LHL is your 1, RHL is your getting the value as your function here, and all these LHD and this LHL and RHL are same. Okay, and the value of the function is also same, which is coming out to be your 1. Okay, so function is continuous at x is equal to 2. Again comes the differentiability. For left hand derivative, limit x approaches to 2 from negative side, like f of x minus f of a upon x minus a, which is your 0 upon some non-zero number, which is 0, and RHD will also be turning out to be as 2. Okay, when you will solve it. So both are not equal, so function not differentiable. So what do we conclude? That we concluded that the function which is continuous at all real values of x, but not exactly continuous and differentiable at 2 points, was your function sum of two modulus functions. Okay, so which was not differentiable at their zeros. Number 22 is, now this is a determinant which you need to differentiate. Now how will you differentiate the determinant? Now looking at these two, you will find that just f dash x, g dash x, h dash x is there and rest is not there. So how it comes? You have to firstly open this determinant. Okay, like y is your fx like this. Okay, mc minus bn minus gx, take this lc minus an, okay, plus hx your lb minus an. Now take the derivative as this is constant, so outside d dx of fx, which is your f dash x, then this lc minus na outside, d dx of gx, which is g dash x, and the last one is here you will take this other constant lb minus ma outside, and d dx of hx is h dash. And this can be rewritten like the determinant again, as you know there is only from here, if this was the value of y, so you can get back it in the form of dy by dx, and you'll just find a change in f dash x, g dash x, h dash x, and when you will expand it, you'll get the same value as you obtained for question number 1. Number 23, as this question type of question we have already done. So if y is equal to e raised to power a cos inverse x, x lying between -1 and 1 show that this function, this equation is equal to 0. Okay, so y is equal to e raised to power a cos inverse x. I have to get dy by dx and second derivative also. So dy by dx is very simple. E raised to power x is having e raised to power x into d dx of this x. So it is e raised to power x into a, and derivative of cos inverse is root 1 minus x square. So it becomes a minus aea cos inverse x upon root 1 minus x square. Okay. So it is suggested, I told you that day also in tan inverse question, that you have to take this root 1 minus x square to this side. Okay. So this question, as this is same as y, okay, so this root 1 minus x square dy by dx becomes minus ay. Now again differentiate it. You will get it as like this root 1 minus x square ddx of dy by dx will be d square y by dx square plus your dy by dx into derivative of this root 1 minus x square, and it is minus a dy by dx. So it is your root 1 minus x square d square y by dx square plus dy by dx into this derivative is 1 upon 2 root x into derivative of this inside function is minus 2x, and it is minus e times dy by dx. So again you multiply with this your LCM, take LCM, so it will be your 1 minus x square, as root and root will be square. Okay, so d square y by dx square, and square means this roots will be removed. Okay, as it will be root 1 minus x square whole square, and minus your x times dy by dx is equal to minus a root 1 minus x square dy by dx. Okay, so this by 2 becomes your minus ay. So it is your minus into minus plus, that is e square y. Take it to other side and you will get this expression as the desired result. So I hope this exercise is clear to you. Practice it well. This miscellaneous exercise cover your all concepts of this continuity and differentiability. I hope this topic is clear to you. Thank you so much.